Okay, great. So we're now relaxed after all that great music and everything. Last class session, we looked at quadratic functions, which are second-degree polynomials, and you have actually a lot of experience with those already. And if I get time today, what I'll do near the end is actually go through deriving the quadratic formula with you and then sort of show you the connection between what you see in the quadratic formula and what you see when you graph a parabola. There's some connections between those things. So today what we want to do is to sort of generalize the idea of, we've looked at linear functions, we've looked at quadratic or second-degree functions, and we want to generalize that to the general class called polynomial functions and be able to quickly be able to draw sketches of those things and not necessarily have to rely on your calculator. Now we'll use the calculator to go ahead and gain some additional insight into how these things are behaving, but we want to mainly be able to do this stuff with our brain. So if we start out with what's called a power function. Now a power function is just simply of this algebraic structure, ax to the n, where n is a positive integer. A positive integer. That would be like 1, 2, 3, 4, 5. And so here's the simplest one, and the a would be a number in front, which was, what's a going to do to the graph of any of the functions here? It's going to, if a is bigger than 1, it'll make it taller and skinnier, similar to what I did here. Here's y equals x. Y equals x. Can you zoom in a little bit with the camera? Okay, so here's y equals x. And then if I look at y equals 2x, that's going to be twice as tall. And you can see at any location x that the dotted graph here is twice as high as the y equals x graph. Now that's very elementary and basic, and in beginning algebra you saw that as the slope of 2. Okay, and in this course we're starting to think of that a little differently. We're thinking of it as a vertical stretch that's occurred to the function y equals x. Okay, then if you go up in power to 2, you're very familiar with that. That's your basic quadratic function. And you could put a multiplier on it and stretch it and maybe even turn it upside down if it was negative, right? Okay, and then finally, if you look at the cubic, we've seen the cubic before, and we can just keep ramping up in the power here. So that family, those things are called power functions. They are single terms, monomials, monomial functions. Single terms of that type of structure. Now, if you start adding some of those power functions together, they don't have to be the same power. You might add a cubic to a quadratic to a linear, and then you get something called a general polynomial function. A general polynomial function. So let's go ahead and play with these today and then see if we, without too much effort, can actually be able to generate the characteristics of the graph and understand the behavior of these things. Is that clear to people so far? Okay. So why don't we start, and I actually wrote some notes down here so I can use my examples today. Let's start with a first degree polynomial. And so that's going to be a what structure? Linear, right? So that's going to be linear in its behavior. And the structure you might see might be something like this, ax to the first power plus b. Now if I write it that way, then a is understood to be what? What do we know a would be? Represent on the graph? The slope, right? Or a vertical stretch factor. Right, the slope of the linear function, or a vertical stretch factor. Now let's go ahead and just put an example with each of these type of polynomials we're going to look at. So let's say we use y equals minus 1/2 x plus 5. Now we know then a quick dirty sketch of that would have a y-intercept at 0, 5, and we label that, and it's going to be falling to the right gradually because it's got only a half. So it would be half as tall as a y equals x graph and upside down. So y equals x would be like where my hand's moving. If I make it half as tall and upside down, it's going to be looking like this, and then lift it up 5. And so we know, thinking in terms of transformations, there's the picture. What's the domain?
All reals.
Negative infinity to infinity, right? And the range?
All reals.
All reals also. Okay, so just keep that in the back of your head. Now, let's look at the second degree polynomials. And you've been doing these first degree ones since beginning algebra. Second degree polynomials in general form, what would be a general way of writing it? Ax squared plus bx plus c, where a, b, and c are constants, numbers, and you've got a lot of experience with this. We'll find out how good your experience is when you do your homework quiz, okay? And the next quiz or exam we have. Now, let's do an example of this one. And why don't I start with one that I start out in factored form? So here's a little simple example that I made up. X minus 3 in factored form times 2x plus 1. Why do I like starting with it in factored form? Why do you think? Because I can see my zeros, can't I? Can't you see the zeros here? Okay, Tyler, what's a zero? At x equals 3. Good. So at x equals 3, we have a 0. Now we're just going to do a little quick micro sketch over here. At x equals 3, we have a 0. And we label it. And then how about Jennifer? How about another 0?
X equals 1/2. Negative 1/2.
Negative 1/2. Good. Negative 1/2 would make this factor turn to 0. So at negative 1/2, and so I come in there and I label that. And if I now multiply this thing out, the way you do that from beginning algebra is you'd say, oh, I'm going to FOIL it, right? First, outside, inside, last. But let me show you a more powerful way to handle multiplying factors in a polynomial together. You look at this mess and you go, when I start multiplying it out, what's the highest degree that you're going to get? What kind of term? X squared. So I start by looking for any combination of the multiplying that would give me x squared. And the only one that would do it here is right there, isn't it? Keep in mind the way I'm presenting this right now, because when I get down here to a third degree or fourth degree, we're going to use this idea. Okay. So I see that the highest power I'm going to get out of this is an x squared, so I look for any x squared terms, and I can see clearly a 2x squared. Now I look for any linear terms, just involving just x. And I look, right here, there's x, 1x, and then here's another pair that gives me x. Okay, so I have a positive 1x, and a minus 6x is minus 5x. So what I'm doing is I'm working my way down from the power that I can see in the polynomial. I'm working my way down in order. And so then finally I look for any constants, and that's only going to come from that last pairing, which is a negative 3. Now what piece of information is useful by looking at this form?
Negative 3. The y-intercept.
The y-intercept, good. At negative 3, because if you zero out x, if you let an input be 0, this disappears, and you're left with a y value of negative 3. So you could go down here on your graph and label that point 0, negative 3 as your y-intercept. Okay. Other things you know about a second degree polynomial is that they have symmetry on their graph. And so this graph then would be coming down through here like this. It's got to bottom out halfway between these points, doesn't it? Between these zeros because of the symmetry of the function. And then it's going to rise back up there. What's the domain of that thing? Domain. All real numbers. Negative infinity to the left, heading to the right, positive infinity. Okay. Notice how we keep repeating all of this vocabulary until it becomes automatic to you. Everybody feeling good? Okay. Let's look at, let's see, I think that's all I wanted to do on that. Let's build this into a cubic now. Now watch this, it gets a little more exciting. Let's go for a third degree polynomial. And here's your general form of your second degree, remember. Here's your general form of your first degree. And for a third degree, it's going to look like some coefficient times x cubed plus some coefficient times an x squared plus some coefficient times x plus some constant on the end. It'd have that kind of structure in descending order. So here's an example. Why don't I use these same two factors? These same two factors. So why don't I take this first factor, and instead of leaving it as a linear factor, why don't I make that a square on that? And then hang on to the other factor, 2x plus 1. 2x plus 1. Feel good? How about the zeros, folks? The zeros of this cubic now.
Plus or minus 3.
Not plus or minus. What would make this y value 0? A choice of just 3. Just 3. Can you keep the flag off of there? Okay. I don't know if you saw that. Okay. So we put the 3 in here, and this zeroes this thing out. Okay? And so only at 3, again, just like on the parabola, that's where a 0 is going to occur, but this time on a cubic, and also at negative 1/2. Negative 1/2. Is that all right with everybody? Okay. So we can now go over again to 3, label that, and over at negative 1/2, label that. I'm trying to model for you good behavior in math, okay? I've been trying to get you to always draw sketches, always label points that you have knowledge of, and then from the sketch you gain insight into your algebra. Okay, so please do that. Your scratch paper on your exams, many of you didn't show me hardly anything. Okay, I want to see it on paper. Okay, so now let's multiply this thing out using the technique for building up building this into its general form like you see up here, the technique I showed you. Now, first of all, probably be a smart idea to take care of this binomial square, which I went through a quick and dirty way of expanding that earlier in the term, several sessions ago. When you see a binomial square, you square the first. You take the product of the terms, negative 3x, and do what? Double it, minus 6x, and then plus square this last term, plus 9. And that quadratic expression now is multiplied times this linear expression. And now let's multiply this thing out. Now, let's see, am I running out of space? A little bit. Let me go down here and expand this. So now I'm looking for any x cubed, right? And I can see there's only one term that's going to give me that, 2x cubed. Now I look for any combinations in the multiplying that give me x squared terms. See if you can do the arithmetic in your head, and I'll see if I can do it in my head, and if we do it right, we'll get the same number.
11 x negative 11.
Yeah, it looks like a minus 12x squared here And then this pairing looks like a plus x squared. So minus 12x squared and an x squared is minus 11x squared. Now look for any linear combinations. 18x. Take 6x away from that and you get 12x, right? Positive 12x. Linear terms. And then any constant is only going to occur from the last product there. Plus 9. So that's a handy, fairly quick, efficient way for you to multiply out and generate this type of form, descending order on that. Okay, let me see if my notes agreed with that. Oh, very good. Okay, all right. So now, you look at this thing and look at this first term. This is a, remember now, I said that this is a sum of several power functions, right? A sum of several power functions that we started with today. So you know what 2x cubed looks like, right? Goes up right and down left. This sort of sets the character for the graph. The leading term sets the character. So you know this thing is going to be up to the right and down to the left from what we studied earlier. So what I do is I come over here and I just put a little arrow there, and then down to the left has to go down here like this. So down left, up right. Everybody comfortable? Okay. Next step is you can see clearly what else on here. What's useful? Y-intercept. Good. Disappear x, let x equal 0, in other words. Gone, 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 and you're left with the y value of 9. So that means we're going to have a y-intercept here at 9. All right. Now, here's something pretty slick. And I mentioned this earlier in one of the sessions, but you may not have heard it. You look back up here at the factored form. And notice at the 0, when x equals 3, that you're going to get a 0. The factor here has an even power. An even power. If the factor has an even power, we say that the multiplicity of this 0 is 2, or even. The multiplicity is even in value. That's the math terminology for it. What I do, the way I think of it, is I think of the graph bouncing off of the axis there. It bounces off of it. Now think about this numerically. What if I was at 3.1 for x? Wouldn't this be a positive value right here? A little bit bigger than 0 if I put a 3.1 in right there? Okay, and what if I put a 2.9 in? Wouldn't 2.9 still give me that same value when I square it? So there's a rising of the y value to either side of this. Now it depends on what happens to this value near that 3. Now if you look at 3, this would be a 7, wouldn't it? So you'd be multiplying the number here that's real close to 3, above or below symmetrically. You're going to multiply whatever positive value you get out of that times whatever this is. The idea embodied there, to make it simple for you, is that the function, this polynomial, is going to bounce off the axis at that location. The question is, does it bounce upward or does it bounce downward? The reason it bounces upward in this case is because we know the graph has characteristics looking down here up to the right, so it has to come down and touch this spot, doesn't it? And because of the even power, it's then going to have to bounce off right there. Bounce off.
So if it was negative 2x cubed, then it would bounce down? Like down?
Yeah, if I had a term here where this term was negative valued near that location, then it would actually be downward. But don't worry about that. I was just kind of showing you why it does what it does. All you have to think of is Winnie the Pooh. Tigger. Boing, 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 right? Bouncing off the axis if the factor has an even numbered exponent. Got it? And you use this end behavior here to help you determine in this case that it comes down. It doesn't cut through there, it bounces off. Okay. Then it's going to have to roll nice and smoothly, and somewhere it's going to peak out. It's going to have to come through 0, 9, and then when it hits this 0 at -1/2, the exponent on that factor is odd. It's going to slice through there like Zorro with a sword. If it's got an odd exponent on the factor at that 0, it's going to cut through the axis. And you can see that this then fits the character of this cubic function. So these extra terms that you see in here cause this graph to wiggle. Instead of it just being a simple power function, 2x cubed, which you're familiar with, just rising up, going through the origin and up the other side. These other terms in here cause this thing to be pulled up higher here and then drop back down over there. And so these other terms in here is what's creating that kind of stuff. That, in a nutshell, is how you look at any polynomial. Okay, any polynomial. And we'll do one more here in just a second. So, notice this thing rises up from the left, peaks out here, and happens to bottom out here. Where a graph changes from increasing to decreasing, or vice versa, going from decreasing to increasing, where it makes that transition, the books call turning points. So those are called turning points. So if you hear questions asking how many turning points does a polynomial have, then you have 2 turning points on this cubic. 2 turning points. And you've already been doing homework with finding maximum locations and minimum locations and how to do that with your technology. Okay? All right, so that's pretty handy. Let's look at one that's then, let's go one more. Let's go to a 4th degree. Fourth degree polynomial. And this is going to have even messier general structure